we're going to do a little bit of reviewing in math, specifically algebra, so just solving equations and scientific notation. So the reason why is because physics is based on math. There is quite a bit of math in here, and so yay for those that love plug and chug type equations where you know what you're given, you plug them in, you're good to go. And then, oh, for those that are more conceptual. But don't worry, in this class we're going to make sure to do quite a bit of math and quite a bit of conceptual so that everyone gets an understanding of what's going on. So the first thing we need to do is review how to manipulate an equation. So the idea is you need to move variables around so that on one side you have the variable you want and on the other side you have everything else. And to do that you have to undo whatever the function was. So for example, if you had something that was added together, to undo addition, you subtract. Need a pen, don't we? There we go. So you need to subtract. If you want to undo subtraction, you do the opposite of that, which is adding. To undo multiplication, you divide, and to undo division, which is the opposite of division, it is multiplying. So you're basically going to do the opposite of whatever it is that you see. So the law of fairness is how we use this idea of doing the opposite. So whatever you do to one side of the equation, you have to do the other. That way it's nice and equal on both sides. So in our example here, we have x plus y equals z, and we're trying to solve for x. And so since it's x plus y, we need to undo addition, and the opposite addition is subtraction. So we're going to subtract y from both sides. So that cancels y out over here, and we're left with x equals z minus y. All right, so just a couple more examples to make sure we're good to go. Solve for a. So a minus b is c, so we're subtracting, so we're going to do the opposite. Addition, so we're going to add b to both sides, cancels out here. We have a equals c plus b. Here we're going to solve for two different ones because it's different with our equation we've got right here. So the first we're going to do is solve for r. Now, does it matter that v and s are together here? No, because that entire expression is added to r. So it's r plus vs. So to get r by itself, we're just simply going to subtract the entire expression vs from both sides. Cancels that out, and we're left with m minus vs. Now to solve for v, we're going to need to do something a little bit different. So I'm going to erase over here. There we go. Go back to my pen in a different color, say green. Solve for v. So r plus vs is the same as vs plus r, so we need to undo addition again. So we're going to this time subtract r from both sides. So it cancels r on this side. And we're left with vs equals m minus r. So now to solve for v, it's v times s, so we have to do the opposite of s, which is dividing. And we have to divide the entire expression on top. So we're left with v equals m minus r over s. And so m minus r is all together over s. So this one's a little bit more fun. Let's give some room here. So now we have a square. Now, for the first part, when we're solving for y, do we care? No. We don't care about the square, except that we have to make sure that whatever we do to one side, we do to the other. So to get y by itself, the first thing we need to do is get rid of this y squared. Or, sorry, get rid of this u squared, not y squared, u squared. So we're dividing by u squared, so we're going to multiply by u squared on both sides. And so that cancels this side out, and we're left with x plus y equals mu squared. And so now we just need to get y by itself, x plus y, so we need to do the opposite there, which is subtracting. So we're going to subtract x from both sides. Again, this is one full expression together. So x cancels here, and we're left with y equals mu squared minus x. So now let's do a fun one. Let's solve for u. And yes, you're going to need to be able to solve for the denominator at some point this semester and next semester as well. So let's go ahead and review it. Let's do purple. Purple's fun. So solving for u, the first thing we need to do is get u by itself. And so we need to get rid of u under here. So we're going to do exactly the same first step. Multiply by u squared. What this does is makes it so that that u squared is gone. So cancels over here, and we have u squared here. So we have x plus y equals mu squared. So now I'm actually going to move it over here. X plus y equals mu squared. All right, so now we need to find u. So we can't get rid of the square yet because we have this m. So it's m times u squared. So we're going to divide by m on both sides. Cancels out here. So x plus y over m. So now we can do with a square. So to get rid of a square, you do the exact opposite of squaring, which is square rooting. And so we're left with u equals the square root of x plus y over m. All right, so the second part of these notes is talking about scientific notation. We're not going to see this until probably about halfway through the semester, but I figured since we're doing a math review, we'd go ahead and review scientific notation as well. So scientific notation is used to simplify very large and very small numbers. And simplify in a scientific term, to me, just kind of means we're a little bit lazy. We don't feel like writing stuff out a whole lot. So the mass of the Earth is 6 with all of these zeros. Now, anyone, whether they're a scientist or not, does not want to write out a number that looks like this every single time. It is very large. It's a lot of work. But instead, if we write it in scientific notation, it's nice and small and compact. 6 times 10 to the 24th. So the same thing can happen here if we're looking at the distance from the Earth to the Sun. We have 146 million kilometers. And again, that's a pretty large number to just keep writing out over and over again. So we simplify it in 1.46 times 10 to the 8th. So what we're going to do is see how to go between these two. So the first thing we're going to do is convert standard numbers to scientific notation. Step 1 is that you have to move the decimal. So here, let's say we have 3 million kilograms. We have an implied decimal point right here. So we need to move this decimal point so that there is only one non-zero. And that's very important, non-zero. One non-zero digit to the left of the decimal. So our first non-zero going from left to right is 3. Happens to be the only non-zero. So what we need to do is make this 3 million a 3. Now, is 3 million and 3 the same? No. If you owed someone $3 million and you gave them $3, they would not be very happy. But that's step 2. We're going to talk about what we do with all of these zeros. So first, let's move our decimal. So we're starting here. We're going to jump it. 1, 2, 3, 4, 5, 6. So we jumped it, moved it 6 places to the left. Now, for very small numbers, we need to do the same thing. So if we start from left to right, our first non-zero is 3. Wow, 3 again, huh? So we're going to jump our decimal point. Here we actually have one. We're going to jump it 1, 2, 3, 4 to get 3.45. So we moved it 4 places to the right. Now, what do we do with these zeros? Step 2, you have to write it where you multiply the number by 10 to an exponent, and the exponent is the number of places you moved it. If you moved it to the left, in this direction, then it's going to be a positive number. So a positive exponent makes a larger number, so 3 versus 3 million, this is much larger. So we need to make sure it goes to a larger value. So 3 times 10 to the 6th, because we moved it 6 places. 1, 2, 3, 4, 5, 6. If we moved it to the right, so started here and we moved it this way to 3.45, then the exponent is negative. So we moved it, review again, 1, 2, 3, 4 places. And since it went to the right, we need to make sure this becomes a small number again. So it's negative 4. 3.45 times 10 to the negative 4 kilograms. If the exponent is positive, it's a much larger number, so it'll be greater than 1. If it's negative, it will be less than 1, or a very small number. So we talked about that, didn't we? Now let's do a couple of examples and we'll move on to the other direction. So we have 1 million meters per second. So we have an implied decimal point right here. And we're going to jump 1, 2, 3, 4, 5, 6, so that we have one digit in front of the decimal point. So 1. And then since we moved it 6 places to the left, we're going to multiply by 10, and it'll be a positive 6 since we moved it left. So here our first non-zero is a 3. So we're going to move our decimal spot 1, 2, 3 places to the right. So that means it'll be a negative exponent. Now can we stop at 3? No, because we have these 4 and 5. So we have to make sure we include all of our significant digits. So 3.45 times 10 to the negative 3 meters per second. So converting from scientific to standard, we're going to do the exact opposite of what we just did. Kind of like in algebra, right? If you want to undo something, you have to do the opposite. So here, since it's a positive number in our scientific notation, we're going to make this number bigger. So we're going to move the decimal spot to the right 4 places. 1, 2, 3, 4. And then we fill in any remaining empty spots with zeros. So that's not empty, that's not empty, but we have 1, 2 spots that are empty. So we get 4, 5, 6, 0, 0 watts. It's very important to make sure you jump all of the spots. So if it's 4, you have to jump 4 places over and fill in those blanks. Because when you get to really small numbers or really large numbers, it makes a difference. So if it's negative, we're going to go to the left. And here it's 10 to the negative 10, so we're going to move this 10 places to the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A really easy shortcut for this is if you're going to the left, you'll always have one less zero than your exponent. So here we have negative 10, which means we should have 9 zeros after the decimal point. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then your 10th spot would be to make that 9.8. All right, so let's do some examples here. So we're going to convert these to standard. It's a positive exponent, which means we're going to go to the right to make a larger number. So 1, 2, 3, 4, 5, 6, and that's where our decimal point ends. So we have 2 spots that have digits, and we have 1, 2, 3, 4 spots that need zeros. So 8, 6, 7, and then 4 zeros. 1, 2, 3, 4 joules. And so we get 8,670,000 joules. Huge number. So now we have a negative exponent, so we're going to move this to the left 7 places. 1, 2, 3, 4, 5, 6, 7. And again, we're going to fill in all those blank spots with zeros. The shortcut is there will always be one less zero than the exponent. So 0.000, 0, 0, 0. So 1, 2, 3, 4, 5, 6. 1 less than 7. 5, 6, 7 meters per second.